optional constant declaration, variable declaration in the statement. Why I'm saying that is optional? So you have to coming back to the constant declaration and variable declaration is definition. And what is that happening? So for the constant declaration, we have a const, that's our reserved word, and following by that, we'll have identifier and equal symbol and numbers. That means we could have defined a constant declaration that directly followed by a assignment to that variable. Okay, but why it is considered as optional constant declarations? Let me ask you this. Why is it considered as optional? It has to be from the grammar, but why the grammar is saying it's optional? Yes? You could have called a variable and you never change it. You technically you don't have to have any constant variables in the input file. That is based on the understanding of grammar, but why the grammar is stating that. There certainly should be some element that indicating it is can be optional. That's coming back to our ED and F, yes.
Because block can be a constant or a variable or a statement, so it doesn't have to be, because like you go from program to block to constant, variable, or statement, you don't have to do, specifically, you don't have to have the constant, it can be a variable or a statement.
Not necessarily correct. But what we have here, the block is with epsilon, we have epsilon here. In the statement, we have epsilon, of course, that is making the statement can be optional. But why the constant declaration can be optional? That's coming back to our foundation understanding towards the EDF, the grammar specification, where the square bracket around it, it means we can match in 0 or 1 time. That means it can be optional. Get it? We can have 0 constant declaration or 1 constant declarations. Okay? But 1 constant declaration, does that mean we can only have 1 constant variable? Can we? Yes, we can have 1 variable. Can we have more constant? But why we can have more? No thoughts? Have you seen this? A curly bracket. The curly bracket in the B and F means we can match in 0 or more times. Now, does that make sense to you right now? We can have more constant. We can have 1. We can have more. It's very similar to our WebEx in your homework, or not homework, in the midterm. We have some of you have faced a question of the number of 2 is 1, 4, 7, and 10. It means we could have 1, 2 at the very beginning or at the very end, at the very beginning followed by 3 2s, encapsulate with a star. 0 or more 3s. Similar idea here. We could have a const with a variable constant that is being assignment, and followed by comma with identifier equal to a number. We can have 0 or more times. Then by the end, for the constant declaration, we have to match the semicolon if we are having a constant declaration. Okay? So that is the idea. The very similar idea applies to our variable declaration. We have var as a reserved word and identifiers followed by another 0 or more identifiers followed by a comma. The pattern is comma identifier. And last symbol and last token, we are doing the example. Okay? But now we come to the question is, can we assign a value to a variable once it's being declared. Similar to C program or Java program, we can have a integer being assigned to 1 or 0 directly once we initialize them. But can we do that here? What? You say yes. No, we cannot. In DL0, why we cannot do that? Simply because the grammar is specified. We can only have an identifier itself. No number being attached. Okay? Then we come into statement. A statement can be assignment statement. Assignment statement we're talking about is identifier, become symbol, that colon equal colon become symbol, and expression. So that is one statement. But we could have more options. We can have begin with in, if, then, while, do, and etc. Okay? But the or here, it means this statement, once we translate into pseudocode, it could be a switch statement. Once the current token is matching to something, it goes directly to that snippet. Could be assignment, could be begin, could be if, could be while, and etc. And the default case in a statement will be what? The default case. What's that? String? The default case is that's all. Basically, we are doing nothing. The default case is we do nothing. Alright? Very good. So once we come into the next part of the grammar, it will have a condition. The condition is either out of the expression or relational testing between two expressions using defined as developed ops will be equal, not equal, less, small equal, or greater than equal. That's relational operations. That's all the condition is talking about. But if you relate it to our homework 3, it's kind of different. Okay? We have even, not odd, here. Just make sure you have multiplier. Okay? Then we come into the expression. Expression here is specifying expression allows operational meaning plus or minus the terms shown by a multiple plus or minus connected by a term. So what exactly it's telling you is we could have a term followed by plus or minus, how many plus or minus terms we could ever have. But then coming to a question, can this grammar dealing with negative numbers? Yes, yes. But which part of the grammar can deal with negative numbers? This one? Or this one? The beginning. Yes. This one is telling you can deal with the negative numbers, positive numbers, and negative numbers. But once coming back to open 3, can we deal with negative numbers? Unfortunately not. That's the grammar specification. We are not dealing with negative numbers. As our homework 1 does not have the negation in your homework 1 instructions process. Get it? Alright. So the next thing is about term. Term is just a term followed by we can have multiple 0 or multiple multiply slash and followed by another factor. And a factor is defined as it could be recognizing an identifier, it can be recognizing a number, or it can be recognizing an open purpose expression, closed purpose. Okay? That's the grammar is specifying. Then lastly, the bottom lines are just defining the tokens. We have number, we have identifier, how they are defined. It's defined by a digit followed by 0 or more digits, and that's for numbers, but the digit is defined as 0 to 9, as you can see, and very similar pattern for the identifiers. Now, what we are focusing here is how we translate one embedding F move into pseudocode. In the yellow line, if the block is saying block becomes block, the program becomes block followed by a period symbol. It's made of, program is made of a block followed by a period symbol. So the colon equal is meaning as is made of. And both program and block are non-terminal. How we know it's non-terminal? The angle bracket. And we know that is non-terminal. Okay. The gray box here is our pseudocode to directly implement the grammar. How is that directly implement our grammar? We know each non-terminal will have an implementation of a function in your true implementation. So it will be a function. So the program itself will be defined as a procedure, a function here in a pseudocode. So once we come into program pseudocode here, we are simply grab the next token. Where you are going to grab the next token, it will be specified in your pseudocode. You just follow that. You don't have to worry about when you need to grab the next token. But exactly the thing we are dealing with here is the block, invocation of block. Why we are invoking a block? Simply because the grammar specifies we have to invoke the block right here. But once we coming back from the block, the token we are checking is what? Period symbol. It has to be a period symbol. Otherwise, it will be going to raise an error telling you about error program must be made of block followed by a period symbol. That's one error message you have seen in the homework week. That is also the error message I demonstrated in our appendix B. Okay. The slides here explains how the grammar rules for expression is translated into a pseudocode. The expressions we are seeing here, the EBF rules is expression becomes an optional plus or minus, followed by a term, then any number of additional plus or minus followed by a term. That is our grammar. But the function here on this slide is named as expression, is a function. Again, each non-terminal must be translated into a function. And we have directly follow the pattern, the grammar here. We enter this function. We first check if the current token is plus or minus. If yes, it will store the current operator and move to the next token and get the next token. Get the next token will invoke the term. Whatever term is invoking, this one, this term. And once we're coming back from the term, we know we have to emit some instructions. Not some instructions will be depending on this operator. This operator is a minus symbol. It means we have to generate a negation instructions, which does not exist in your homework 1. So do not generate this part. If you generate this part, it will be error. Okay? Simply your program does not recognize it. And once we come back from if the token is not plus or minus symbol, simply we can imagine zero times this set, it directly goes to the term. The term will be this one. And once we come back from term, we know we have to process something. That processing will be followed by a while loop. So why we define a while loop is based on the curly bracket. The curly bracket is telling you we could imagine 0 or more times. That means we are going to implement a while loop. But what is the while loop condition? It will be directly following the first element we are seeing. The first element will be plus or minus symbols, basically matching this graph. And we are checking, okay, if it's plus or minus symbol, then we get into the while loop. Check, save the current token, and grab the next token. Once we grab the next token, we are invoking the term. Okay, term. When we're coming back from term, we don't care what the term has on what. This is not our business. But here we only consider about the expression expression instruction generations. And once we're coming back from the term, we are just checking this token, the same the token is what. It is the plus symbol, and we are just emitting the operator for the plus instructions. And if it's minus symbol, we're just emitting the minus instructions. And then we're coming back to the question is, emitting. What exactly emitting? Is emitting telling you, emitting the instruction directly to a terminal, or emitting that instruction directly to the ELF file, or something else? Is it emitting the instruction to a temporary array to save all kinds of instructions? Is it directly generating instructions, or is it saving that instruction to a temporary memory location? You have two options. What? Now you can guess. Yes? Saving that in array. That's a good guess. That is indeed what we are having here. So this slide is just introducing how the intermediate code and or the P code is generated. We see here is one instruction example that is load, L, and N. So load is, of course, we have already known that as a loading instruction, or loading a variable's value from the memory and going to the top of the stack. And three parts in an instruction will be OP, L, and N, corresponding to the instruction format. OP, we know, is operation code, and here is load. And L is lexicographic level or lexical level. And what is it? What is the level we're dealing with the load instruction? Is it dealing with static link or dynamic? Recognizing everything. Static link or dynamic link? A or B? Dynamic? You sure? Dynamic? So it is not dynamic. Static. Just randomly select one. 50%. Okay. It is static. But what is static?
Zero is like the current calculation level, the calculation level you are, and if you get one, is one now.
Simply think about actually coming to your actual implementation. You have been very good at programming, right? I'm just making this assumption. You are very good at programming. So if we're having two independent functions, one function is called A, one function is called B, okay? A and B. If we have a local variable for A, function A, we have a variable S. A local function variable B, we have a local variable Y. But if we know function A is calling function B, can we use variable Y in function A? What's that? You can? No, you cannot. You cannot. Simply they are just local variables. Local variables is not accessible by the other functions that is independent from each other. Okay? What they can access is what the variables is above them. One lexicographic level above them. For example, we have defined a global variable, for example, Z. Global variable Z is living in lexicographic level. And those two functions is basically the physical child of the global environment. That is why we can ask the global variable Z there. That's called static link. Okay? Dynamic link is A is calling B. That's called dynamic link. Okay? Don't confuse them. So the L here is referring to the static link accessing. Alright, lexicographic level. So the N here is just a memory address offset. What exactly it means here? Well, you'll read. It means we are loading some variables in the current acceleration vector. the current activation rate at index 3. Alright? So each time a new instruction is generated, it's stored in a code segment, and the code index CX here, as you can see here, CX is incremented by 1. The CX is served as a pointer to the next instruction slot in our code array. And so the code generator emits, whenever it's emitting the load 03, just basically stored in the current available slot that the CX is pointing to. That's it. And based on that saving, then we can raise the CX by 1 to indicating what is the next available slot we can store new instructions. And based on that, so then I have another very interesting question is, what is the data structure we are dealing with for this code segment, the test segment? Is it 1D array or 2D array? In this case. Yes.
Would it be a 2D array because you need to put more commands underneath that initial load when going down?
Correct. It is 2D array. 2D array. Why is 2D array? Because simply because we are storing everything, one instructions, everything, 3 elements on a single line. It means we could have n by 3 matrix to store that information in 2D array. If you're telling me, okay, it's a 1D array, that makes sense. If it's 1D array, CS plus 1 is nothing. You are just from an opcode to the lexicographic level. Is that the next available slot for you to store more instructions? No. But let's be coming back from this one, and the code segment just grows sequentially as more P code instructions are produced. And this process is the foundational for our intermediate representations, IR. Okay, remember, intermediate representation, IR. I don't want you to confuse what is IR in our virtual machine and what is IR here. And intermediate representation and the virtual instructions list will later be executed by your PM0 virtual machine. And at the very bottom, we can see an exact sample for a statement as A becomes B plus C. This compilation will eventually produce a sequence of load, store, automatic instructions in the same way as we saw here. Okay? So I think it's a good way to stop right here, and we must be coming back on Wednesday. We will talk more. All right?